We start our video by considering two infinite series. And please look at my terminology here. Let's say you are given an infinite series with the terms an, and of course, sometimes maybe some terms are negative, right? It doesn't have to be all terms positive all the time. Anyway, if some terms are negative, then we can look at the corresponding series, which is the second series we consider here, where all the terms take the absolute value of the original term here. And in general, the two series are different if some terms are negative here. For example, so please look at the current example. It is an infinite series where some terms are negative and there's an alternating sign change, right? Because it's like plus, minus, and so on. And the corresponding series in the second one actually means that you have to take out the negative sign whenever the negative sign appears. For example, the absolute value of all these terms means that all of these now are positive basically. You see, and of course these two series are not the same. And you can try to determine whether they are convergent or divergent. For example, let's do the second one first. And you can notice that this one is basically just the harmonic series. And we have learned that by the P series test because the P is 1 inside the P series, 1 over n to the power fixed power P. And because of this, when the P is 1, we understand that it must be divergent. That's the P series test. However, for the first one, we are not using the P series test because P series test requires that all the terms have the positive sign. But in this case now, it is actually an alternating series, right? And it's alternating series test we can use. So there are two conditions we have to care. The first condition is that we have to take the limit of the individual term because we can actually write our current series in terms of the summation notation like this. So it means that for the condition 1 in the alternating series test, we can take the limit 1 over n for n goes to infinity. So it becomes 0. And it satisfies the condition 1. How about the condition 2? The condition 2 basically means you have to check that the sequence of numbers here are all decreasing. And I think it's quite obvious that all of these are decreasing now if you write down all the terms inside the sequence. So there's no doubt both conditions are satisfied. It means that the first series we consider is actually convergent based on the alternating series test, right? Now you can see these two series may not have the same behavior because my original series now by the alternating series test is actually convergent. However, for the second series, it's actually divergent by the P series test. So now, let's make some notes here. It's actually easy to notice that when all the terms an are positive, and both series we consider are the same, right? So there's nothing special about it. We don't have to differentiate the two series in that case. And let's look at the point number 2. So you can use the last example as a hint. The fact is that for any infinite series, I'm giving it to you. In general, when you take out the negative sign and change it to positive sign for each term, of course, the absolute version of the original infinite series is bigger than the original series, right? I'm talking about the sum of all numbers. So I think this fact is actually quite natural to understand. And because of the fact that just like the last example, we saw the case that the behavior of the two series actually are not the same. So it makes sense that we give it a new name depending on whether the behavior of these two series are the same or not. So let me write it down here as point number 3. So please look at the 3 definitions here I've just made. If both infinite series are convergent, from now on we'll call it an absolutely convergent series. If it happens that the original series is convergent, but the absolute version of it is actually divergent, we call it a conditionally convergent series. And in the last case, it's obvious. When both are divergent, we just call it divergent. The series given at the beginning, we have mentioned, this one is actually a conditionally convergent series because of the fact that the absolute version of it in this current case is actually the harmonic series. This one itself is divergent, right? But we understand that as an alternating series, this one itself is convergent. So overall, we call it a conditionally convergent series if the behavior are not the same for the both series here. And we'll introduce a test today about the problem on the absolute convergence and conditionally convergence. So let me go to a new page here. So please look at what I've written down here. The fact is that the current test, we call it the ratio test because essentially you're looking at the ratio of the neighboring terms. When you take the ratio, we look at what's happening to the absolute value of ratio when we take limit n goes to infinity. And we call this one the big R to stand for the ratio test. And if you do the computation for this ratio, and if you notice that it is less than 1, we understand that actually the infinite series is an absolutely convergent series. And if the ratio is bigger than 1, it is a divergent series. However, if the ratio is actually equal to 1, it is the tricky case here. It means our ratio test does not work. And no conclusion means you don't know the answer by the ratio test. But in that case, you have to search for the answer separately based on the two series you have in that case. And let's look at some examples together now. Please look at the current problem. You see, I'm giving you an infinite series. I would like to ask for more things in this problem. So it's not just about whether the current series is convergent or not. I would like to ask whether it is absolutely convergent or conditionally convergent or divergent. It means this problem essentially you have to consider both series, right? Based on the definition of absolutely convergence, conditionally convergence, and so on. And let's try to apply the new test we have just learned, which is the ratio test. Let's try to see what's happening. Ratio test means you have to look at the ratio you have. And please take a look at the terms given. This term is basically an. And the fact is that whenever you apply the absolute value sign, we can forget about the sign change term from -1 to the power n, right? So I can write it as for the bottom, which is an, I can simply forget about the -1 to the power n. So the bottom is just n squared divided by 3 to the power n, and the top is the term an plus 1, which means that I can replace the n by n plus 1, you see, and the n by n plus 1 here. So basically, you have to do some simplification based on the fraction at the top, and also the fraction at the bottom, I can actually flip it, right, to make it looks like 3 to the power n divided by n squared. Now, I hope that you can see that you can actually cancel out some terms. For example, n copies of 3 can be cancelled. So you're left with only one copy of 3 in the bottom. And in that case, we can look at the ratio term, which is the big R, which is basically we take the limit n goes to infinity for whatever we have in this simplified fraction. So now the fraction inside the absolute value sign is actually having the numerator n plus 1 squared at the top. The bottom is just the same as 3 times n squared. And I think we can do this calculation quite easily because you see the fact is that this fraction is the same as n squared plus 2n plus 1 at the top after expanding the bracket by the square term divided by n squared. And we understand that as a rational function in n, when n goes to infinity, only the highest power term matters, which means we can make it look like n squared divided by 3n squared, which means actually the answer to this limit is actually 1 over 3, right? And based on the ratio test criterion, we understand that because the ratio is less than 1, so our current series is actually absolutely convergent. So that's the end to this problem. And so please look at the current problem. Once again, I'm asking for something more. And as absolutely convergent, conditionally convergent, or divergent for the current series, it essentially you have to consider both series. And as I said, we can try to use the ratio test to attack the problem because it is convenient. If the ratio we find is actually less than 1 or bigger than 1, the bad thing about the ratio test is it does not solve all type of problems. In the worst case, when the ratio is 1, we cannot do anything and we have to go back to the basic series test we have learned for the series, the first one and the second one separately. But anyway, for the current one, let's take a look at the ratio test. So if you look at the ratio test, you have to look at basically this ratio. And once again, I can drop the sign change term. So it means the bottom becomes 7 to the power n divided by n factorial. That's the bottom. How about the top? I can change whatever you have the n to be n plus 1, right? So which means the top is 7 to the power n plus 1 divided by n plus 1 factorial. So now I can flip the fraction in the bottom and we can talk about how to do the cancellation now. First of all, please look at the term with the base 7. You see n copies of 7 can be cancelled. So you're left with only one copy of 7 at the top. And how about this? And let me write it in the green color on the left hand side. You're basically having n factorial divided by n plus 1 factorial, right? And based on the definition of the factorial, the top actually now has n factors, 1 times 2 to n. The bottom has one more factor because you're multiplying 1 times 2 times n, and one more which is n plus 1, right? And you can cancel out all these factors. So it means after the cancellation, you're left with only one extra factor in the bottom, which is the biggest integer n plus 1. So same here. We are left with only n plus 1 in the bottom. So it means that after the cancellation, the simplified fraction becomes 7 divided by n plus 1, right? And the ratio term, we have to take the limit n goes to infinity for 7 divided by n plus 1. And because we understand that conceptually, it looks like 7 divided by infinity, right? So any constant divided by infinity conceptually means it is 0. And we have learned it before already. And anyway, let's look at the ratio test criterion when the ratio is actually 0, which is less than 1. And by the ratio test, we understand that the current problem is actually absolutely convergent. And once again, absolutely convergent basically means both series we consider in the top left corner, both are convergent. And let's look at another example now. And please look at the current problem if I'm asking whether it is absolutely convergent or conditionally convergent or divergent. And I hope you can see what's happening if you try to apply the ratio test. So let's do it together. When you use the ratio test, you're looking at the ratio like this. And basically, an term is this one. And we can drop the negative sign when we try to simplify that because we are doing it under the absolute sign. So the bottom is just the same as 1 over n squared, and top is 1 over n plus 1 squared, right? So I can flip the fraction in the bottom to get n squared over 1. You see, and now let's do the limit n goes to infinity for the fraction inside the absolute value sign. You see, the fact is that when you do this, basically you're having n squared divided by n squared plus 2n plus 1 in the bottom, and you're taking limit n goes to infinity. And the fact is that, you see, because n goes to infinity, we only care about the dominating term, which is n squared divided by n squared. And we get that it is 1, right? So it essentially means the limit actually gives us 1. And as we have seen already, I told you that for the ratio test criterion, when r is 1, there's no conclusion. It means we are not getting any answer when the r is 1. So what can we do about it? We can only go back to the original understanding of the series. For example, let's consider the original series. It is the same as the alternating series like this. And we can actually use the alternating series test here. In this case, there are two conditions to check for the alternating series test. The first condition is you have to take the limit n goes to infinity for 1 over n squared, which is of course the same as 0. And for the second condition, you have to make sure that the given sequence is actually decreasing. But I think it's obvious for 1 over n squared. So it means that this series itself is actually convergent. How about the absolute version of this? So the absolute version of this series is actually like the summation of 1 over n squared without the sign change term, of course. And I believe you can tell me this one is convergent also because by the p series, now our series looks exactly like a p series, and the p is actually 2, which is bigger than 1. And by the p series test, we understand that this series is actually convergent. And please look at the two answers you have. You see, for both the series we consider, both are convergent, which means that if we combine our answer here for the two series, we understand that actually an absolutely convergent series because of the fact that both are convergent. And it's only one example when the ratio is 1. Of course, when the ratio is 1, it can happen that both series are divergent, or maybe it can happen that it is conditionally convergent. And that's the end of this video.